Okay, so in the last lecture, we talked a little bit about vector magnetic potential. We saw in what kind of things we can use vector magnetic potential. We said that we can use vector magnetic potential in order to calculate the value of B for a little bit more complex structures. We said that we can calculate the value of flux by using vector magnetic potential, or we can use it to calculate the values of inductances that we will study in the future. In the end of that lecture, we said that in this lecture we will talk about magnetic properties of materials, and I emphasized on the importance of knowing the tiny little details, the things that and forces a material to behave in a certain way under the vicinity of any external magnetic field. What is it? What is the main thing that urges a material to behave in a certain way whenever there is a magnetic field? Just like we can compare this to the electric field, and we knew that whenever there is an electric field, that the electron is going to be is going to flow in the opposite direction of that electric field. That was pretty easy for us to understand, because we knew that electric field basically enforces electric field implements a force on a conductor, and that force basically moves or accelerates or dislocates that charge. So that was pretty easy for us to understand, but in this case things are going to be a little bit more complex, because this is not as simple as it was in electrostatics for electric field and electrical behavior of the material. So the topic for today is magnetic properties of materials. So he's saying that magnetic field, reflecting back once again to a circular loop that we studied. We talked about it that whenever a current will flow in a circular loop, as a result, there will be a magnetic field that will be generated by that flow of current, and we saw that the current carrying coil, or that circular loop which was carrying the current, the behavior of that coil was similar to a bar magnet. The loop could be regarded as a dipole with north and south poles, just like we did with a solenoid, just like we did with a bar magnet. So he's saying that the magnetic field is always going to be in the form of closed loop, and that circular loop can be what we'll say about this, that circular loop can be called a magnetic dipole, because there was a part in which the magnetic lines of force was departing. We will say that that part is north pole, and there was a part in which the magnetic fields were entering, and we'll say that that is the south pole, and we talked about it, and we said that it is just like a bar magnet. So he's saying that magnetic moment for a loop of area A, we studied that also, that magnetic moment for a loop of area A is going to be M is equals to IA. Okay, and we extrapolated it, or we changed or modified this expression further by saying that if that loop has n turns, then this equation will further be modified into NIA, or if we want it to be a vector, will say that this is n hat NIA, and this n hat basically shows us the direction which is perpendicular to the plane which is carrying loop, or we can say that this is perpendicular to the area. So he's saying that the direction of this magnetic moment was normal to the plane of loop with right hand rule. Now coming back to the things that corresponds to the value of, corresponds to the behavior of the material. He's saying that magnetization in a material is associated with atomic current loop generated by two mechanisms. He's saying that if you take a look, if you take a deep look into the atom itself, you'll see that uh, what was happening in that circular loop. When we were talking about a circular loop, a current carrying circular loop, and we were saying that it mimics a bar magnet. We were saying that there is a north pole above that circular loop, and there was a south pole below that circular loop, and we called that circular loop had a magnetic moment. He's saying that whenever we dive into the structure of the atom itself, we'll see that what's happening in the structure of the atom is that the electron is basically moving in orbits. So if you compare these two things, the current in that circular loop and the electron that is moving in orbits, these are two pretty similar things, don't you think? uh, the electron is moving in orbit, and if that electron is in fact moving in that orbit, then as a result there will be some kind of magnetic force, or there will be a magnetic moment of that electron which is orbiting the nucleus. So he's saying that magnetization in a material is basically associated with atomic current loop. Now there are two types of currents. One, the electron is orbiting the nucleus, that corresponds to the circular loop, and the other, which is way less as compared to the orbital motion, is due to the spinning of electrons itself. So he's saying that these are the two mechanisms uh, which govern the magnetization in a material. So the first mechanism that governs the magnetization of material is orbital motion. Orbital motion of electrons, okay, around the nucleus. Similar motion of protons around each other inside the nucleus. And the second thing is spinning of electrons. So the electron spins around its axis just like the earth spins. So he's saying that the magnetic moment of an electron is both due to its motion and due to the spinning. The magnetic behavior of a material is governed by interaction of magnetic poles of its atoms, magnetic poles, magnetic moments of its atoms with the external B. He's saying that if there are, for example, if we are talking about hydrogen atom and there is an electron which is rotating in the orbit, which is moving in the orbit, which is doing an orbital motion around the nucleus. As a result, we were saying that due to the motion of that electrons in that orbit, there will be a magnetic moment. So there will be a magnetic moment of an atom, a what will you say, a cumulative magnetic moment of that atom. Will add up all the magnetic moments, and as a result what we'll get is the cumulative magnetic moment of that atom. He's saying that the little thing that we were talking about, that how a material acts in a certain way under the vicinity of an external magnetic field, he's saying that that thing is because of that magnetic moment, that cumulative magnetic moment of an atom, and the interaction of that magnetic moment with external magnetic field. Now we have two things. We know that whenever there is a magnetic field and there is a structure, a thing which has magnetic moment, as a result that external magnetic field will interact with that thing according to its magnetic moment, and uh, that magnetic moment will force that atom to behave in a certain way. So he's saying that this behavior, magnetic behavior of a material, is governed by the interaction of magnetic moments of its atom with the external magnetic field. So he's saying that this behavior, which depends on the crystalline structure, this basically it depends on the crystalline structure. We don't know how those atoms are made for different conductors or for different materials, and that basically what that depends on is their crystalline structure. If they are fixed, if they cannot move, uh, their magnetic moment or their atoms will not, or their domains will not be able to align themselves according to the external magnetic field, just like dielectrics, when the electrons were too uh, so tightly bound that they were not allowed to move under the vicinity of an external electric field. The same case is here. He's saying that the behavior of the material basically depends on the crystalline structure. That is the basis of classifying materials, as we have three classifications. We can say diamagnetic materials, we can say paramagnetic materials, and we can say ferromagnetic materials. Paramagnetic and ferromagnetic. So in these two types, the atoms have permanent magnetic moments. Now you can compare these types of materials to electrostatics, or the types of materials like we studied in electrostatics. Uh, we talked about the materials which had permanent electric dipole moments, polar materials, and we also talked about some things in which there were no there were uh, the absence of permanent magnetic moments, non-polar materials. We said that whenever they are placed in the vicinity of an external electric field, the poles are induced, and whenever that field is removed, the poles vanish. So paramagnetic and ferromagnetic materials are the type of materials which has permanent magnetic moments, which has permanent values of m's, but they are a lot different from each other. We will explain that later. But in the diamagnetic materials, there is no permanent magnetic moment. Permanent magnetic dipole moments. Okay, so diving into orbital and spin magnetic moments. Still, we just have discussed what are the things that govern this. So we'll have to study a little bit in detail about these orbital and spin motions, and we will use now some kind of equation so that we can explain what's happening here. So orbital and spin magnetic moments. The goal is for us to understand why a material behaves in a certain way when it is placed under the vicinity of an external magnetic field. So first of all, we'll try to study the orbital motion in a little bit more depth. So he's saying that classical model of atom, we have circular motion. In the more advanced type of models, that circle is basically changed by the elliptical orbits and so on and so forth. And then we talked about that there is no obvious motion of electrons, there is a probability of electrons, but that debate goes further into the quantum mechanics or quantum physics. So that is not the scope of this course. We won't be talking about that thing. We will consider the classical model because in electromagnetic field theory, we are not diving that deep into the structure of atomic structure of a material. We just need to understand why a material behaves in a certain way. So he's saying that we'll consider classical model of an atom in which the movement of the electrons or the orbits of the electrons are circular and they move around the nucleus. And this thing basically extend to more quantum mechanical model of atom by incorporating prediction. So he's saying that electron basically, now we need to understand, we need to quantify what we have talked about earlier, the orbital motion of electrons. We need to quantify the magnetic moment that is being produced due to the motion of that electron around a nucleus in an orbit. So he's saying that in order to do that, we know that electron has a charge minus e, it is moving with a constant velocity u, we know that too, in a circle of radius r. If we say that this is a nucleus and this is how an electron is moving, so we can say that this is the radius r and this is an electron whose charge is minus e, and this is moving with a velocity u. So he is saying that it will complete one revolution in the time period. What will be the value of time period? The time period is 2 pi r over u. So 2 pi r is basically one revolution and u is its velocity. So he's saying that as a result this of this tiny current loop with current I, what will be the value of current I that is flowing due to this motion of electron in this circular orbit? We can say that I will be equals to, we know that I is equals to q over t. So I will be equals to minus e over t, and if we put the value of t here, we can say that I is equals to minus e u over 2 pi r. We have calculated the value of I. Why are we calculating the value of I? Because we need to find the value of magnetic moment, and in order to calculate the value of magnetic moment we need to know the value of I, and we need to know the value of A too. Okay, so I is equals to minus EU over 2 pi r, and if we want to calculate the value of magnetic moment, that is going to be IA. So we'll put the value of I, which is minus EU divided by 2 pi r, and we will put the value of A, which is going to be pi r square in this case. So this will simplify and take the form of this equation minus EUR over 2. So this is basically the value of magnetic moment that is being produced due to the motion of this electron in this orbit by when it is moving with an orbital velocity of u. Now he is introducing another concept here. He is saying that LE is basically ME, U and R. What's this? This is angular momentum. Angular momentum of electron. So ME is basically mass, and U are the things that you already understand. So LE, the angular momentum, he's saying that even once again we will talk about angular momentum of electron. We will talk about the value of angular momentum of electron, but we will not go deep into this concept because this concept corresponds to quantum physics. So what he's saying is that angular momentum, according to quantum physics, orbital angular momentum is quantized. Okay, so quantum physics says that the orbital angular momentum is not continuous, it is basically quantized, it is discrete. Okay, so to be very specific, he says that the value of LE according to quantum physics, as it is not continuous, as it is discrete, he is saying that LE will always be the integer multiple of LE is going to be the integer multiple of this H type symbol. I can't remember the name of this symbol. If someone knows, please let me know. I know that this basically corresponds to Planck's constant. So he's saying that the angular momentum needs to be the integer multiple of the Planck's constant, and the Planck's constant is h over 2 pi. So if you put the value of Planck's constant h here and calculate the value or divided by 2 pi, we will get a value, and we will say that it is angular momentum will always be an integer multiple of this thing. Why are we doing this? We wanted to know the value of magnetic moment of the orbital motion, hence the subscript O, and we calculated that. So why are we doing this? Why are we talking about angular momentum? We're talking about angular momentum because this is the magnetic moment for a single electron, but it is not going to be this if there are multiple electrons. So he's saying that is simplifying it further. He's saying that as LE can only be an integer multiple of this thing. So LE should be either it should be 0 or it should be H or it should be 2H hat or it should be 3H hat, similarly so on and so forth. So what will be the minimum value of MO for a single electron? For that case, what you'll have to do is that we will need to modify this equation according to angular momentum. If we want to modify this equation for angular momentum, what do we need? We have U, we have U, we have R, we have R. What we don't have is M. So what we'll do is we will multiply this equation with ME and we will divide this equation with ME. Now we have U, we have R, we have M. We can replace this and modify this equation and write this as minus E over 2ME into LE. Now we have written this angular moment, we have written this magnetic moment in the form of angular momentum, and if we want to calculate the minimum value of this magnetic moment, what we'll do is we'll put the value of LE to be this H hat only. This is the minimum value. If this is not the minimum value, then the magnetic moment is going to be 0. So the minimum value for orbital velocity will be orbital magnetic moment will be minus E H hat divided by 2ME. So this is the minimum angular, this is the minimum magnetic moment for a single electron. So he's saying that now, despite all the materials have electrons and all the electrons have masses, some are non-magnetic and some are magnetic. Why is it so? Because we know that there are a lot of materials and all materials have atoms and all atoms have electrons, and if all of them have all the same things, then why are some materials magnetic and the others are not magnetic or non-magnetic materials? He's saying that the reason behind that is that in the absence of external magnetic field, the atoms of most materials are oriented randomly, just like we talked about uh, the behavior of materials during electrostatics. And whenever they are oriented randomly, the net magnetic moments, the net orbital magnetic moments generated by these electrons, they cancel each other out and they become equal to 0 or they are very small. Okay. In addition to orbit, spin magnetic moments also comes into play. We talked about that earlier. We said that this was only a single thing. There was another thing which was spinning. He's saying that in addition to the orbit, spin magnetic moment ms also comes into account, and that is magnetic moment for spinning is the minimum value is the same to me, but this thing does not have major contribution in the behavior of materials. Why is it so? He is saying that electrons of atoms, such atoms which have even number of electrons and they exist in pairs, and whenever there are two electrons, they exist in pairs, the spin of one electron is usually opposite to the spin of other electron, and as a result the magnetic moment due to the spinning of first electron will cancel out the spinning the spinning magnetic moment of the other electron, and as a result the total magnetic moment for spinning is going to be 0 for the atoms which have even number of electrons, and even though some of them have odd number of electrons, the only spin magnetic moment will be that single electron which is left out, which doesn't have a pair. It will be because of that. So the orbital magnetic moment will have a major contribution because they are not canceling each other out. But when we talk about spinning magnetic moment, they will cancel each other out, and as a result the contribution of spinning magnetic moment in the behavior of a material under the vicinity of any external magnetic field is going to be very tiny as compared to the contribution of orbital magnetic moment. So he is saying that yes, another reason behind the tiny contribution of spinning magnetic moment is the nucleus also spins. So he's saying that the spinning magnetic moment of any particle is inversely proportional to its mass. So nucleus has a greater mass, and so as a result, the spinning magnetic moment is itself already small, even if there is no one else to cancel that effect. But it is very small due to larger mass of the nucleus itself. So as a result, we have two different reasons. The reason for spinning for less contribution of spinning magnetic moment of electrons is the pairs, the canceling each other out thing, and the reason behind the less contribution of spinning magnetic moment of a nucleus is due to its heavier mass. So he's saying that the main thing that is governing the behavior of any magnetic material is the orbital magnetic moment. So I hope you somewhat understood why materials behave in a certain way. We this topic is still not over. We will talk about magnetic permeability, but we have a rough understanding as to why a material acts in a certain way. So if we talk about magnetic permeability now, what we're going to do is we're going to shape these concepts into a certain terminology that we can relate to when we talk about the behavior of a magnetic material. So magnetic permeability is that term which basically quantifies sorry, which basically tells us that how this material will behave. So when we talk about magnetic permeability, he's saying that if we say that that the property is the magnetization, the property of behaving, of responding to an external magnetic field is magnetization. So magnetization is obviously a vector. The magnetization vector of a material can be defined as, now you need to know we are defining a major characteristic. That characteristic is magnetization vector. He's saying according to whatever we have studied so far, the magnetization vector, which is the characteristic of a of a material, it can be defined as vector sum of dipole moments of atoms contained in a unit volume of material. So basically, the vector sum of all the dipole moments of atoms that are contained in a unit volume. That vector sum will be called magnetization vector, and it will be depicted by m hat. So he's saying that magnetic flux corresponding to now there are two different fluxes. One flux is due to the external magnetic field that we applied, and the other flux is due to the magnetization of that material itself. So he's saying that magnetic flux corresponding to m, that will be bm. This magnetic field is due to the magnetization of the material itself. That will be equals to mu naught m. Okay, and if there is any external magnetic field present, the magnetic flux density due to that external magnetic field is going to be mu naught h. So he's saying that whenever we place a material under the vicinity of an external magnetic field and the atoms have aligned themselves according to that external magnetic field, then in order to calculate the value of total magnetic flux, we have to take into account the magnetization of that material plus the external magnetic field. Okay, so we have bm and we have b external. What is bm? Bm is mu naught m, and b external is mu naught h. Okay, so if we take mu naught common, we can say that m plus h comes inside. So this is the value of b. Here m corresponds to the magnetization of the material itself, and h corresponds to the external magnetic field, that external magnetic field intensity that we applied. So he's saying that generically or in general, in response, basically this magnetization also appeared due to the presence of this uh, external magnetic field. So he's saying that M is basically due to the is in response to the external field H which is applied. So generally that M is directly proportional to H. If the amount of H that is provided externally it increases, the magnetization will increase. The more and more atoms will align itself in the direction of the external magnetic field, and as a result this M will increase. So we can say that this M is equals to susceptibility into H. We can relate this thing with the concept that we studied in electrostatics also. So he is saying that this xm is basically magnetic susceptibility of the material. We have defined susceptibility in electrostatics earlier. We said that it is basically uh, the capability of a material to change itself according to the externally applied field. So diamagnetic, and this susceptibility is basically dimensionless quantity. As you can see that this M magnetization and this magnetic field intensity, both of these have the same units. So he's saying that in diamagnetic materials, we have paramagnetic materials. He's saying that in diamagnetic materials and in paramagnetic materials, the value of susceptibility is constant at a given temperature. You need to keep this in mind always, that in diamagnetic and paramagnetic materials the value of susceptibility will always be constant. And what does that tell us? This tell us that the relationship between M and H is going to be linear always. Whenever we increase the value of H, the value of M will increase. Whenever we'll decrease the value of H, the value of M will decrease. It means that if this thing is constant, then these two things are linearly related to each other. But what if this value, this susceptibility's value is not constant? This is not constant in ferromagnetic materials case. What will happen then? As a result, if we increase this value and this starts decreasing, then this magnetic field is going to be uh, the value of this magnetic field will increment less as compared to this H. As a result, the relationship between M and H will not be linear, because now there are two things that are changing, and these two things will have an effect on the value of M. So he's saying that in diamagnetic and paramagnetic materials, the relationship between magnetization vector and the externally applied magnetic field intensity, it will always be linear, just like this. But in ferromagnetic material, this the value of magnetic susceptibility will not be constant, and as a result this relation will not be linear. It will be linear to some extent, but after reaching saturation this linearity will be converted into non-linearity. So he's saying that for ferromagnetic material, the things are going to be a little bit different. So you need to understand this, that in diamagnetic and paramagnetic materials, the relationship between H and M will always be linear. So he's saying that what if we consider this thing for dia and paramagnetic materials only. So we'll talk about ferromagnetic materials separately. He's saying that B is now mu naught H plus susceptibility into H. Once again, we'll take H common. We'll say that mu naught H 1 plus susceptibility, or we can say that this is equals to mu H, such that mu is equals to mu naught 1 plus susceptibility. You can explain this just like we explained the value of permittivity back in electrostatics. So we will not waste much time on this thing. Whenever we want to calculate the value of relative permeability, we know that relative permeability is the permeability of that material with respect to the permittivity of free space, permeability of free space. So the permeability of that material is mu naught 1 plus susceptibility divided by mu naught. These two things will cancel each other, so relative permeability will be 1 plus susceptibility, magnetic susceptibility. And this is it. Just to take a little bit idea of things, I will urge you to see the table that is given. You will see that for diamagnetic materials, dia, para, and ferro, you will see that for diamagnetic materials and for paramagnetic materials, the value of relative permeability will approximately be equals to 1 always. For diamagnetic, the value of xm will be negative, and for para it will be positive, but for both of them the value will be 10 raised power minus 5's order. This is the value of magnetic susceptibility. But whenever we will talk about ferromagnetic material, the value of susceptibility will be far greater than 1. This tells, and relative permeability will also be far greater than 1. This tells us that how strong the ferromagnetic materials have the magnetic characteristics. Okay, so diamagnetic and paramagnetic will always be of the order of 10 raised power minus 5. The susceptibility of these two materials will always be of the order of 10 raised power minus 5, and relative permittivity will always be approximately equals to 1. This thing means that the diamagnetic materials and paramagnetic materials permeability will be very close to the value of air. But when we talk about ferromagnetic materials, the relative permittivity will be much larger than 1. It means that it will be much stronger as compared to air itself. So this is it for today. In the next lecture, we will talk about ferromagnetic materials in a little bit detail. Thank you so much. If you have any questions, you can ask them in interactive session.